Good afternoon, everyone. This is Michael Remaley. In today's video, we're going to be going over hurricane forecasting. This is lab number 1 in a multi-part series, and during this multi-part series, you are going to learn how to become a more experienced and better hurricane forecaster for the upcoming tropical weather events. So the very first requirement in a tropical cyclone, if you're going to want a hurricane or a tropical storm, you're really going to need some warm water first and foremost. Now, typically the water needs to be at least about 26 degrees Celsius or about 78.8 degrees Fahrenheit or greater in order for there to be a substantial chance of tropical cyclone formation. If you look here on the bottom right hand side of the screen, you can see the very skin temperature of the water. And what this really shows us is the water temperature at the very top of that surface there. So you can see in the Eastern Atlantic, for example, the water temperatures are running at about 27 degrees Celsius. Now, if you look conversely in portions of the Caribbean, water temperatures are actually running fairly high at about 28 to 29, even some 30 degrees Celsius waters. This is a fairly warm water for tropical cyclones to thrive off on. However, if you conversely take a look at portions, let's just say over the Canadian Maritimes, you can see the water temperatures there in degrees Celsius are actually nearing the freezing mark. Freezing is at about 0 degrees Celsius or 32 Fahrenheit. Now, the warm water also, and this is a big thing, it must absolutely extend deep down below the surface by about 50 to 100 meters deep in the ocean. And this is known as the upper ocean heat content, which we'll talk about here in the following slides. So what is upper ocean heat content? Well, upper ocean heat content is characterized as the depth of the warm water content. And very simply here, the deeper the warm water extends below the surface, the greater the values are. And this is also going to increase the potential energy for hurricanes to take advantage of. Potential energy is very important because if you can get a higher potential energy value, you can create more intense hurricanes in a theoretical environment. Now, upper ocean heat content values must at least be about 10 kilograms per centimeter in order for there to be a storm or a hurricane to take advantage of the water at depth. If the values are under this threshold of 10 kilograms per centimeter, those values are typically going to be insufficient for a storm to intensify significantly in that environment. And over the next 2 slides, we're going to be covering the examples of high upper ocean heat content and a low upper ocean heat content environment. Now, high upper ocean heat content is characterized generally by values that are greater than about 55 kilograms per centimeter. And this is very important because here, if you look at the upper ocean heat content based on yesterday's map, actually, based on the map as of November 17th, and we're looking here in the Caribbean. And, if you've been watching our Hurricane Outlook and discussions, we talk a lot about the upper ocean heat content in this part of the world, given the recent storms. Now, what you can see here is values that are typically shaded in the greens, yellows, oranges, and reds, and the whites are going to be your high upper ocean heat content environments. And everywhere within basically the center of the screen is in a fairly high upper ocean heat content environment, where values are typically ranging from about 75 kilograms per centimeter all the way up to about 125 kilograms per centimeter. Now, what this really is, and what this really is telling us here, the signal, is that the warm water, the 8.8 degrees Fahrenheit layer, the 26 Celsius layer, is actually going down at a fairly significant depth in the water. So what's happening is as a hurricane comes along through here, let's say a hurricane comes along and through here, it's a powerful Category 5. What that's going to do is it's going to try to upwell cooler water. However, with these very warm upper ocean heat content values that are deep at depth, what you end up having is a storm that only continues to churn up this water. As it's upwelling, it's only upwelling warmer water. So the values never go under that magical 26 degree isotherm line, that 26 degree or 26 degrees Celsius kind of threshold. That's very important in upper ocean heat content environments such as this are very supportive for rapidly intensifying hurricanes. Now, if we look out here in the Eastern Pacific, now the values are going to be skewed because they range from 0 to 220 kilograms per centimeter. But you can see areas where the upper ocean heat content environment, especially in the Central Pacific, would be fairly low. You can see values out here basically to the south and east of the Baja of California are generally characterized as a very low upper ocean heat content environment with values ranging from about 20 to about 45 kilograms per centimeter. And this is very important because you get a tropical cyclone to move into that environment, it is not going to thrive super well. And the reason for that is because as it's kind of churning across there, what it ends up doing is upwelling cooler water. And at some point, it's going to upwell water that is not 26 degrees Celsius. It's going to upwell water that might be 24 degrees Celsius instead of that 26 or 77.8 degrees Fahrenheit. That threshold, once it is below that threshold, what you typically end up having is a storm that has its inner core completely collapse because a storm cannot keep generating substantial convection around its axis of rotation in order for pressures to continue to fall and the storm to continue to intensify. And what you can see out here closer to Mexico, however, you can see these values are on the order of about 60 to about 85 kilograms per centimeter. These values would be supportive of intense hurricanes in this environment, but not category fives. You would typically see storms capped out right around category 3 to low end category 4, still very dangerous, but not a category 5 hurricane like you would get right now in the Caribbean. So the general tropical cyclone tracks. What do you need in order for, or what's going to happen when these storms, come out into the water? Well, first of all, in order to understand that, we got to know where these tropical cyclones are first created. These tropical cyclones first start from a tropical wave located over the interior parts of Africa, usually over portions like Nigeria, etc. These are just basically everyday thunderstorms that develop over these portions of the environment, uh, but they kind of keep on going. These tropical waves are in a very moist environment and they can create their own pocket, at least, of energy to sustain themselves for a few days. And now you typically will see these thunderstorms pulse up during the diurnal cycle, which we'll talk about more in lab number 2. But first of all, these waves usually take about 5 to 10 days to get from land to water. Not always, but usually. And once they get out into the open Atlantic, they typically take about 1 or 3 different types of tracks here. You can see the first two, and what I should note here is these are based on the 1950 to 2015 climatology. So these are based on a multi-decadal period of time where the average tracks are kind of shown here. And now you can see in the yellow and orange lines, you typically get storms that will move out generally into the open Atlantic. The yellow line is a little bit closer and could impact portions like Bermuda. However, typically you do not see a significant threat to land from this. However, in years where we have strong areas of high pressure, which has been this year, etc., even 2017, for example, remember Irma, you can get tracks that come further south and do not turn out into the open Atlantic. In this instance here, you can see the red line is denoted as heading towards the Lesser Antilles. And this is basically kind of your far southern axis here, where storms can usually track into out across the open Atlantic. However, that's not the only areas where tropical cyclones can form. Sometimes you'll end up getting storms that form in the Caribbean or the Gulf of Mexico. Uh, the Usually what happens is earlier or later in the hurricane season, tropical cyclones can spin up in the Gulf of Mexico or the Caribbean. These storms are usually going to be the most intense and pose the greatest threat to land. The reason why? Well, you can see that in this part of the world, you have a ton of land masses that are around here. Unlike the open Atlantic, you have a lot more land masses and a smaller area for these storms to track and a smaller margin of error for these storms to track within for them to not hit land. It is basically impossible for a storm to not ever hit land or cause impacts in this part of the world here. Now, Storms that form from this part of the world typically, not always, but typically originate from non tropical areas of background vorticity. Late in the year, especially Central American gyres can form. Now, what these Central American gyres are, these are CAGs for short. These are just background areas of spin or vorticity in the atmosphere. And if you've watched our hurricane outlook and discussions over the past several months, you'll hear me occasionally talk about a gyre or a Central American gyre. That is basically what we're talking about here. These storms typically form from Central American gyres, and they can usually spin up in any sort of location, but typically here in the Central Caribbean. Now, sometimes what will happen, not usually, but sometimes what will happen out of these Central American gyres is a little area of spin will try to create a thunderstorm and break off into their own standalone energy source. This is typically when you'll start to get the formation of a tropical depression or storm in this type of environment, especially with Central American gyres. Now, again, you can see a range of outcomes here are possible, anywhere from a storm track like we just saw with Hurricane Eta and Hurricane Iota to a track that exists similar to one maybe like Wilma or Matthew or Michael, where those storms end up coming into the Gulf of Mexico and threatening portions of Florida. And there's also a possibility of a storm directly going into the Gulf of Honduras and affecting portions like Belize and the Yucatan Peninsula. Now, the final requirement here, in order for a tropical cyclone and hurricane to really thrive, if it wants to be able to build thunderstorms near the center, the vertical wind shear must be very low. Now, what is the vertical wind shear? Vertical wind shear is characterized as a change in direction and speed with height. Now, you can see here in the two diagrams, we have directional shear and we have speed shear. Directional shear is on the left, speed shear is on the right. Now, with directional shear, as one would kind of think, the wind direction is going to change with height. So as you go higher up in the atmosphere, the wind direction is going to change. So in this particular diagram, you'll have wind coming out of the northwest, and at the very top here at about 200 millibars, or at about 39,000 feet, you'll have wind that is typically cruising towards the north and east. So you have that change of direction. Now, one might think, well, tornadoes require directional shear and speed shear. Now, that is very true, but for hurricanes, especially tropical cyclones and hurricanes, in order for these storms to be able to build around an axis of low pressure, the vertical shear has to be low. And the reason because of this is if you have a ton of directional shear, these thunderstorms will actually get blown off into one direction. These will get blown off away from the axis of rotation. And what this causes is the storms cannot perfectly build that eye wall. They cannot continue to lower the pressures in the atmosphere. And that causes the storm to eventually basically either hold steady or rapidly weaken with time. They can see also the speed shear here is that the wind speed is going to change with height. So you can see again there at the very surface, at about, the very surface, you have relatively light winds. And then up at the very top here, you have fairly strong winds. And these are basically horizontal areas of wind. Well, again, what one might think is, well, why does it work for tornadoes and not hurricanes? Again, it all goes back to the way the hurricane is kind of positioned. It all has to deal with how the hurricane develops and how a hurricane thrives. Again, a hurricane, in order to develop a well developed inner core structure and an eye wall, if you have thunderstorms that are basically being pushed off to one side, what you'll end up getting is storms that cannot completely close off that eye wall, and you only have storms on one part of that side. Now, these storms will still be very intense, but they do not efficiently work to lower the pressures required for storms to intensify further. So you both need directional and speed shear to be relatively low in the environment. And in the upcoming, in the upcoming lab sessions, what we'll be talking about here is storm environments that have low and high shear and how that will generally affect storms in that type of environment. We'll also talk about dry air versus moist air, etc., in the upcoming presentations and labs. I hope you guys did go to enjoy this. And again, if you guys did, make sure to go check out the other rest of my videos that I do on tropical cyclones and hurricanes if you guys want to learn more and understand. Finally, this is all the common sources. Most of the graphics here were created by me. If you guys do need to use these graphics for any sort of information, my contact email is listed there for rights to use my graphics that I made. That being said, I hope you all have a great rest of your afternoon and evening. Of course, I am Michael Remaley. I'll talk to you guys again some more later.